Okay, so we'll look at reviewing a little bit the main results from Spirit and Opportunity as part of this. I want to put their results into a broader historical context about the story we are building up about how water on Mars has changed over time. And we'll do that and then try to also wrap up a couple of topics about where we find water on Mars currently. Because where we find water on Mars currently is clearly important if we want to continue to look for whether there is still life on Mars or if there was life on Mars. And where there's water on Mars is obviously important for human exploration. Okay, so just to recap the Opportunity mission, where was Opportunity sent to? What? Yeah, but much more specific site.
Eagle Crater?
Yes, Eagle Crater is where it landed. So it was sent to the Meridiani Plains and happened to land in this small crater where it made some discoveries that relate to the question of whether there was life, whether there was water available on Mars in the past, and has been going for the past 11 years and essentially is now in a whole new environment. I won't try to draw out from you. I mean, the instruments we're talking about, we have various spectrophotometers that will look for different kinds of elements, different kinds of mineral compounds. There's a thermal emission spectrophotometer on the mast, the PanCam mast that sticks up from the rover that can read the infrared radiation coming off of rocks and interpret what minerals are in those rocks. There were 2 spectrophotometers on the robotic arm. The Mossbauer looks specifically for iron-containing compounds, and the alpha proton X-ray spectrophotometer, the APX-S, looks for different kinds of elements. It can identify, calcium and iron and magnesium and other kinds of elemental signatures. There are microscopes that provide up close, detailed view of the rocks, because the texture of the rocks, the structure of the rocks can also provide an indication of what was going on when those rocks were created. Both Spirit and Opportunity were very much focused on finding sedimentary rocks, because those are associated with materials that are laid down possibly in aqueous environments or by windblown environments. And so just in general, how does looking at rocks on Mars today let us build up a picture of whether or not there was water flowing around Meridiani Plains 3 billion years ago?
Because water would create certain features in the land and leave certain minerals and certain.
Okay, so yeah, it's a process of looking at the evidence we can see today and inferring back what were the environmental conditions that led to the creation of those features in those rocks, what the minerals that were laid down, the fine structure of the rock. So, Opportunity lands in Spirit and Eagle Crater, finds evidence for hematite in those concretions, what are colloquially called blueberries, these little round mineral formations that are embedded in the layers of rock at Eagle Crater. On Earth, Hematite primarily forms in the presence of water. There are some ways that it can form without water, but the fact that Opportunity actually found that is good evidence for water. There are other minerals, jarosite in particular, that were detected by the instruments on the robotic arm. And we know jarosite has to be laid down or created in an aqueous environment, in an environment that's got water. So these features here provided good evidence for there being groundwater at this site. Water percolating up through the existing sediments could have led to the formation of these concretions, these little blueberry structures, could have resulted in the formation of this jarosite mineral, could have resulted in the distribution of minerals and different kinds of ions throughout the different layers of the sediment that reflect the idea that there was groundwater flowing through this area and moving these different sulfates and chlorides and other minerals and other compounds around. So that's all evidence for groundwater, which is interesting, but doesn't make us particularly jump up and down, because even today on Mars we might expect that there would be the conditions that would allow groundwater to be available down at depth in the under the surface. But the team also found these structures that are very characteristic of water, of sediments that are laid down by flowing water. These cross-bedded patterns of different layers of in the sediment. And if I could have shown you the clips, we'd see another view of that to reinforce that. But that merited its own press conference, because now we're talking about surface water. However, this is not necessarily a really benign, nice environment that Opportunity is providing evidence for. This water, from all of the evidence in these minerals that we're looking at in the early part of the mission, was very acidic water. Probably leached a lot of iron out of the rocks. So you'll have to imagine, because you can't see the nice little animated clip that was in the excerpt from the movie, imagine a series of rolling sand dunes, maybe, southern Arizona, northern Baja California kind of low playa beach kind of environment, where you have these shallow pools of very acidic water with high concentrations of iron and sulfate minerals, and gentle Martian breeze blowing across the surface here, moving the sediments around, laying down these deposits. It's an environment where on Earth we might expect to find organisms that are capable of living there. So habitable, yes, but it's a pretty extreme environment, and it's possibly not the kind of environment we would expect life to originate. So if life was already present on Mars, it might have been able to cope with these kinds of extreme conditions, but it's not the kind of really nice environment where you would perhaps expect life to form. Currently, now that we're in year 11, Opportunity is now exploring Endeavour Crater. And what's important here is that whereas all of this Meridiani Planum, the sites that Opportunity looked at initially in these Meridiani plains is all sort of the Hesperian era. That middle transitional time in Mars's history. Endeavour Crater, since it's a large crater, has actually excavated deeper, older sediments and going back to the Noachian era. And why is that important? What do we think early Mars might have been like?
I mean, early Mars is a little more promising for water life in general. So
Right.
we can find like a time capsule of that in the older sediments.
I like that, time capsule. Okay, so yeah, we have some ideas that early Mars in the Noachian might have been wetter, might have been warmer, might have been more habitable. And so, the fact that Opportunity has lasted so long has allowed the mission to actually explore this whole new area on Mars that allows a window on a much earlier time period in all of the discoveries that might lead to. Spirit, the landing site was Gusev Crater. Gusev Crater has a large channel emptying into it. This looks like one of those river-carved channels. And so if there were a river running into this crater, what would you expect to have formed in that crater? A lake. Okay, and lake with the water would lead to lake bottom sediments being laid down, and that was the whole reason for sending the Spirit there.
How long did that take? How long did that take from its landing site to getting to Gusev Crater?
It landed in Gusev Crater.
Oh, okay.
Gusev Crater is large. You have to target large safe places to land, and so Meridiani Planum is kind of like a big parking lot. So Opportunity had an easy time landing. Gusev Crater is still very large enough that the bottom area of the crater is not it's level. It has small rocks, things that the airbags and the rover bouncing to a halt on the surface could deal with. But initial findings were very disappointing because all of the rocks that they found in the immediate area around the landing site were essentially basaltic lava. So if indeed there was lake bottom sediments in Gusev Crater at one point, over the billions of years since that time, the whole bottom has been covered over by lava flows, and if there are sedimentary deposits there, they're not available. So Spirit was sent on a trek, essentially. It's only meant to go something like 600 meters for 90 sols, 90 Martian days. And they very rapidly realized that there wasn't anything interesting to look at where they landed. There were hills on the horizon, kilometers away. And so they sent Spirit off not knowing whether it would survive long enough to make it to the hills. Had to survive through a Martian winter in order to get to the Columbia Hills, but eventually found...
Those are the hills named after the astronauts.
Yeah. Yeah, so there were 7 of these hills in this outcrop, 7 astronauts on Columbia, and Spirit primarily spent its time going up and around Husband Hill, which is named after the mission commander who was lost on that mission. Anyway, Spirit found various salt deposits that you would expect to be laid down in an aqueous environment. They found silica that you would expect to be laid down in hydrothermal environments. And, if you've got a hydrothermal environment, you've got heat, and you've got water, you've got minerals. It's like the hydrothermal springs out in Yellowstone. Those are areas that people are very interested in terms of what microbes might be living there. And Spirit also found evidence for carbonates, which has been a big question mark. If Mars did have an ocean and an atmosphere of carbon dioxide, it should be producing lots of sediments of carbonates like our ocean does. The White Cliffs of Dover and coral reefs and other kinds of carbonate deposits. It's been very difficult to find carbonates on Mars from orbit. Possibly the carbonate deposits are all covered over by dust that covers the whole planet. Possibly Mars's ocean was too acidic for carbonates to be formed, but it was an important finding of Spirit that it found these carbonates. Okay, so I want to put these findings into a broader context, and to do that we're going to go to orbit. Because the landers obviously can only look at a couple of individual spots on the planet. So it's always good to complement the findings that we're finding from the ground with a broader view that we can get from satellites orbiting around. Don't want to go into the details here of how this all works, but Mars Express has an instrument called Omega, and Mars Reconnaissance Orbiter has an instrument called CRISM. And these are, again, spectrophotometers. They measure how much light is coming off of the surface in these different wavelengths. This is a little misleading. It's not like these spacecraft are zapping the planet with colored light and getting some bouncing back. This is just natural infrared and visible, primarily light that is naturally reflecting off of the rocks on the surface of the planet. And what these instruments do, they can for any given location on Mars as it passes over, tell how much is being, how much light is coming off in these different wavelengths. Everything, as I said, from infrared through visible light. And by looking at the spectra that can be derived from those, how much near infrared, how much far infrared, how much red, how much yellow, how much green light is coming off of these minerals, and very fine gradations in between, can indicate whether the rock contains olivine or feldspar or other kinds of minerals. And so these instruments are basically mineralogical mappers from orbit, and they can identify all sorts of compounds of interest. And what I want to focus on in particular for the rest of this talk is minerals that, as we've talked about, indicate the presence of water. Infrared light is especially useful for identifying minerals because the kinds of atoms that are in a mineral and how they are bonded together influence what wavelengths of infrared light the minerals absorb and what wavelengths of infrared light the minerals will emit and what they just will bounce off and reflect. There's lots of mechanisms for molecules to absorb and release infrared radiation depending on the vibrations of the atoms in the mineral. Don't worry about it. Just, feldspar will absorb a different set of infrared wavelengths compared to olivine, which will absorb a different set of wavelengths of infrared light. Some of the things that we're particularly interested in finding are hydrated minerals. Okay, so some minerals have the ability to either incorporate water or not as they are formed. And of course, the more water is around during their formation, the more water they will incorporate into the mineral lattice. Clays are very important signatures as well. Many minerals, as they weather in response to water, will turn into different kinds of clays. And there are more different kinds of clays than you are interested in learning about. But just say clay equals mineral has been broken down partially by water. So if we can identify clays from orbit, those are areas on Mars where water has been active in the past. If we can identify hydrated minerals from orbit, those are areas where water has been active on Mars in the past. Yeah.
Like clay's like moist, so does it have water in it?
Clays may or may not be moist. I mean, they're formed by the action of water on minerals. But if you take a piece of clay and bake it in an oven, it's not going to be, all that water can come off. It's still a clay. Chemically, structurally, it's still a clay. You can still identify it as a clay, whether it's got water bound up into it or not. So, the detail on this slide is not important at all because it's not the actual real data we want to look at. I just wanted to point out that these instruments send up data about dozens or hundreds of different wavelengths of infrared invisible light coming up from a particular area. This is more information than we can process, visually very easily. So the basic approach here is to say, well, if I'm going to identify olivine, which is a mineral I'm interested in because it breaks down in the presence of water, so if I see extensive deposits of olivine, it means there hasn't been a lot of activity of water there. I know that olivine will absorb infrared radiation at certain wavelengths and not absorb it in others. So I can take those particular wavelengths of infrared light, translate them into visual light colors that I can actually look at, and make false color images that will allow me to see where I might find olivine in this landscape. Yeah.
Wait, so this is just showing you the difference in all of that data?
Right. So these are just different slices of the data coming from these two different sites. And the point is here, you've got to essentially take these data to process it to create these kind of false color images so that you, as a human with an eye that's only responsive to visible light and not to infrared light, can make sense of the data that's being displayed on the map here. Now, if we had eyes that could see in the infrared, we'd have a much different view of the world. We'd be able to do some of this mineral identification without the use of all of these instruments and computers and so forth. Just to give you an idea of how this works, here's some data from, and I can always never remember how to pronounce this. I just say Marwith Vallis. It's one of the sites that was considered for the opportunity for the Curiosity rover, the Mars Science Laboratory. On the left, well, you should be able to tell what data is presented on the left there. What data does that look like that we've seen time and time again? Elevation data. Okay, so this is the Mola elevation data on the left. So you can see that there's some obvious craters. There's a lower area up in the upper left. There's some highland areas if you go down to the lower right. You know, this is just one section of Marwith Vallis. But if you take that data that's coming up from, I forget whether this is Chrism or Omega data, and process it, you can identify where you would find hydrated minerals. So these colored areas, these colored patches are deposits on the surface of Mars in this area that we can tell have hydrated minerals in them. And if you look, at least these, this big assemblage of hydrated minerals here somewhat traces out this channel that's going from the medium level elevations down to those lowlands. So what would we expect to have flowed through this channel in the past? That might relate to the presence of hydrated minerals in that area today. Water, okay. So you put the two data sets together, and it gives us a pretty good story that, well, there might have been water flowing through this channel in the past. Here is some of this kind of data from Endeavour Crater, again from orbit. And you know, as I said, this large crater is interesting because it presumably has dug up deeper sediments that go back into the Noachian time period. And these phyllosilicates here, when you see phyllosilicate, basically think clay. Okay, and so from orbit, a number of deposits have been identified that are high in clay-bearing minerals. And so when Opportunity finally made its way across the plain to Endeavour Crater, it hit Cape York here. It spent a lot of, more than a year investigating different sites around Cape York, but has been progressively, will be moving down toward this area where these very interesting signatures are being seen from orbit. Okay. So to put this all into some framework, we've talked about three main geological eras: the early Noachian, and then the Hesperian, where things seem to be changing over time, and then the current Amazonian era, which tends to be cold and dry and primarily dominated by winds blowing across the landscape. If you look broadly from orbit, you tend to see deposits with clays primarily in geological deposits that go back to this Noachian period. So, you know, the fact that there are clays there, clays not only indicate water, but fairly neutral to basic, to somewhat alkaline water. Environments that we would consider to be quite habitable. As we look at deposits that date back to the Hesperian, we see more things like sulfates and other deposits of sulfate-bearing salt minerals, which kind of indicates things are drying out. Things are becoming more acidic. The fact that we have these sulfate deposits means the environment is becoming less and less habitable. And then anhydrous ferrous oxide, basically rusty sand all over being blown around Mars, is what we currently have today. There are terms that have been applied to those time periods. Phyllosian, because phyllosilicates are clays. I won't expect you to remember that. This term here relates to the sulfates, and this term here relates to the iron oxides that are present today. So these mineral investigations kind of building up a story of a Mars that started out fairly habitable, a fairly neutral aqueous environment producing clays and other kinds of sediments, and then over time Mars just gets progressively drier, more acidic, less and less hospitable, less and less habitable over time until we get to the Mars that we see today. And that's primarily why Gale Crater with this Mount Sharp was selected as the site for the Curiosity mission. The nice thing about this Mount Sharp hill in the middle of Gale Crater is that the sedimentary layers in that Mount Sharp presumably record all of these changing environments over time. And so what Curiosity will specifically be spending the next several years doing, now that it has finally gotten to Mount Sharp, after looking at some other interesting things in Gale Crater, will be essentially gradually moving its way up these layers to do the kinds of chemical and mineralogical and other analyses that the lab was sent to Mars to carry out. So the first layers that the Curiosity rover will look at when it gets to Mount Sharp will be the youngest or the oldest layers? The oldest layers. Okay, that's down at the bottom. They're going to be the oldest, presumably Noachian aged layers, full of clay minerals. And then as it works its way up the slope here, it's going to be able to look at progressively younger and younger sediments to really give us a good description of exactly how the conditions on Mars changed from 4 billion years ago to 2 billion years ago, at least. So I couldn't show you the clip from the roving Mars, but let me get out of here and go into YouTube again and show you this clip from the Maven mission, which is NASA's most recent mission to Mars, which is looking at the loss of Mars's atmosphere over time and how that atmospheric loss might have played into this habitat change that we've been able to build up with the mineralogical information.